Thank you all for joining us today. We are excited to be here and bring you on a virtual tour of our work. We are Haptek Lab, and we're pleased to present our work entitled Beyond the Surface, the Behavior of Digital Ceramics. In this project, Haptek Lab uses industrial robotic arms to push industrial ceramic manufacturing beyond the surface. So our work challenges the disconnect between digital fabrication and the haptic qualities of material behavior and develops a digital materiality based on tactile robotic feedback rooted in craft traditions. The team seen here is comprised of a consortium of artists, architects, technologists, interior designers, academics, and practitioners based in Toronto, New York, and California. We met throughout the year, sometimes in person, but more recently mostly via Zoom. The largest cohort of the team is based at Ryerson School of Interior Design, and thankfully that group was permitted to return to the Ryerson Creative Technology Lab at FCAD around mid-July, where we've been continuing our physical studies, and you can see that here in Zoom with the robot in one of the screens. The team developed design research questions to establish parameters and expectations for our research on digital material behavior, asking, how can we translate the haptic qualities of handmaking via digital craft? And further, how can the material behavior of digital ceramics create new opportunities and possibilities beyond handmaking and beyond simply the performance optimization of handmaking effects? Drawing on our diverse backgrounds in both ceramic arts and fabrication craft, it was critically important for us to integrate robotic processes in a way that imbues the haptic qualities of handmade ceramics. The images scrolling on the screen are some of our studies, which we will discuss later in this presentation. In tackling this problem of translating haptic, emotive qualities into digital making, we looked at both ceramic arts and historical architectural ceramic projects, most of which were crafted by hand. Looking at the experience of architectural ceramics is really to understand the building skin as a surface that produces a phenomenological experience at two scales, the tactile scale and the optical scale. These interactions with the building surface are part of the urban experience, walking down a sidewalk or viewing a building across the street or a few blocks away. Our goal was to embed the surface with both detail at a small scale and narrative at a large scale, to enable multiple readings at different points of view. In this Chapel of Souls in Porto, Portugal, for example, the individual tiles, each with incredible detail, aggregate together to create lively scenes. Across the street, we can more clearly see the stories of saints' lives depicted at the scale of rooms. Further away from the building, the details become textures in rich blues, which give depth to the building's surfaces and vibrancy to the context. This phenomenon is one example of Leatherborough's term surface architecture, which points to the building facade as an instrument of identity and engaging its surroundings. Simply put, building surfaces communicate. Harnessing this potential proved to be fertile grounds for us in this project, where we were asking questions about legibility and meaning, and ways to achieve these in architectural ceramics. Historical architectural ceramic projects ranging from those by Louis Sullivan to Ethos Boccaio demonstrate that clay is a productive medium for creating architectural effects, including color, texture, diffusion, and reflectance. Textures from rough to smooth can generate a sense of depth. In addition to architectural precedents, we also turn to those from ceramic arts to unpack qualities that engage the viewer haptically. Reflecting on these traditions, we began at the tactile scale by working with the clay by hand, looking at typical forms of making, like casting, stamping, molding, and bas-relief, to create detailed ornamental tactility. Starting from the standard set of clay tools, we worked intuitively to produce haptic surfaces through multi-layered textures. Recording manual manipulations of clay allowed us to observe the behavior of the terracotta clay body and record impressions made by human touch. Because of the density of the clay and the need for speed in the factory setting, we realized that the robot was a critical partner when scaling up haptic processes to industrial fabrication. Our next step was to transition towards recreating these haptic tactile experiences through the robotic arm. Here we can see our very first experiments with the robotic tooling on Boston Valley Terra Cotta's standard terracotta extrusions. We simply attached a ceramic hand tool to the end of the robotic arm to mimic hand marks. It became immediately clear that direct translation between the hand and the robot would need skill development in terms of operation, material behavior, and produced effects. At this stage, the robot was operated using manual controls to better understand the forces the robot exerted on the clay. The clay used in Boston Valley Terra Cotta's manufactured products is extremely dense, so the robot provides strength to manipulate it, up to 150 kilograms of force. However, because of its strength, it essentially treats the clay as a non-material. It carves through it without sensing how the clay is behaving, or even sensing that it is there at all. And so we needed to develop a process to program craft and materiality into the tooling that teaches the robot to account for the behavior of the clay. We saw great potential in making use of the robotic arm in an industrial post-extrusion process, which would develop a new kind of digitally tooled haptic experience. We found that layering impressions in the clay created a richer surface and chance material behavior. This is one of our first custom-made end effectors. The repetition and slight variation in terms of the tooling and the way we overlapped clay marks to create variations in material behavior, we're starting to come close to developing craft skill in the robot to mimic our initial hand manipulations. We then simultaneously approached the project from another perspective, the optical distance. For this aspect, we worked with an image that could operate at an architectural or urban scale. Using an image from the archives of the Erie Canal Museum of Syracuse, we tested various ways the image could be made through impressions in the clay surface. Working with wet, unfired terracotta extrusions from the factory, we explored the use of common hand stamping tools, like these embossed 3D printed rollers. Multiple rollers were printed using variations of height field images wrapped on the roller surface. An array of 3D printed end effectors were designed and fabricated at various scales, lengths, widths, and depths in order to test the legibility and textural qualities of the impressions. One such exploration was the role of color in image legibility and haptic qualities. Applying terra sigillata allowed us to create layers of color, providing contrast and therefore legibility at various distances. We were also interested in the indexical relationship between clay, color, and the physicality of sites of extraction. We explored using clay from the banks that feed the Erie Canal to produce the sigillata, so the colors would reveal the materiality of the site itself in both a symbolic and embodied way. We then explored a variety of 3D printed rollers, differing in scale and geometry. Throughout the experimentation, we sought to create and test legibility of the image at varying distances. We found a depth limitation in this process. To be legible from afar, the roller needs to be scaled proportionally in depth. This is not always possible within the thin surface of the extrusion panel, as we can see in this chart. We also explored different types of roller geometries, including those that would roll in a non-linear manner to produce surface tessellation patterns simply through rolling. This included an oloid roller, tricylinder rollers, and wobbly rollers, which are cylindrical rollers clipped at various angles to roll along a wave-like line. Ultimately, we found we were limited by the roller. As the image gets larger, it was difficult to embed the density of details required to produce tactile qualities at a haptic distance. What became evident is that the embossed roller method images seemed to only work well when scaled at a single terracotta panel. When we tried to scale up the roller to produce an image across multiple panels, not only was this highly uneconomical in terms of roller material required, but also insufficient in terms of the legibility from afar and the haptic qualities from up close. Here we encountered a common problem of digital fabrication and design. Digital images can be infinitely detailed, but those nuances don't translate to clay in the same way. Clay doesn't always want to be digitally precise, and digital 3D modeling is unable to precisely simulate the behavior of clay. Instead, all materials are quasi-non-materials, materials who have no character and no behavior. Yet, clay deforms. Its moisture shapes how it forms ridges and builds up, how it sticks to the tool or peels off. This unpredictability was precisely our interest in the digital process, and so we returned to some of our early tooling methods, learning from the pressure required to affect the surface typography. We fabricated a series of tools as extensions of the robotic arm. We found the more compelling textures to be those that suggested pointillist paintings and bas-relief sculptures, textures that are familiar and haptic. This type of craft sensibility allows us to move beyond the novelty of the robotic technology towards an artistic end, one of our team's primary goals. At the same time, we saw the potential for this method to produce a type of digital manufacturing economy. Any image or textual pattern could be programmed at the same cost using the same tools. With the robotic arm, the economy of production is no longer that of matrices, no longer finding economy by making numerous identical copies from molds or stamps. Instead, the logic of automation uses economy of movement, where each movement per second costs the same as any other movement. And with the capability of moving at a pace of 2.3 meters per second, programming custom images for robotic stippling had scalability potential. In our early attempts at using this method to create an image, the results fell flat, literally. Seen here in this image is a panel tooling of someone you might all know at ACAW 2017. This early test didn't leave room for a feedback loop between the digital design process and the material behavior that corresponds. Here, the terracotta panel was still being treated like a non-material. Tooling was based on images produced in a grasshopper script, which assigned various diameters of circles based on light and shadow. This was directly applied as a tool depth to the clay surface using a tapered pick to make impressions. The resulting panel was not compelling materially, nor were the images even legible. And so we realized that we needed to stop trying to predict or control the outcome of the digitally tooled clay. Instead, like we did by hand, we started by simply making marks, this time through various randomized computationally scripted points. Just as an artist might repeatedly make the same action to see what might shake out, we also treated the digital process in the same way, developing a feedback loop between the haptic qualities produced rather than trying to make the clay conform to a premeditated image. We started from a series of densely packed gridded points and moved towards random seed-generated points, varying both density, spacing, depths, and radii of marks. We also developed a 5-sided tool making use of the 6 axes of movement of the robotic arm for continuous tooling of varying marks. In this way, with our robot collaborator, we began building skills over time with training, in the form of altering programming and tools, to exploit the central qualities of the resulting material effects and produce a feedback loop. Dense and overlapping marks, the scale of fingerprints, on slip-colored clay created literal and phenomenological depth to the surface. We evaluated these surfaces based on surface qualities and textures, matte and gloss finishes, its potential to catch light, and how it might reflect its surrounding environment. In this regard, we were also interested in how these digital haptic terracotta surfaces might also interact with other reflective materials, namely glass. Reconsidering the tooled terracotta extrusion as a mold, a series of experiments were conducted at Corning Museum of Glass to explore how our digitally tooled surfaces might inform the behavior of molten glass. First, a cavity mold was created for a blown glass vessel. The tooled faces were set up to form a cavity and clamped tight, and pre-coated with graphite release agent. A calibration tool was used to pre-size and pre-shape a molten glass bubble, which was then lowered into the cavity and blown using a blowpipe. The vessel was rolled, centered, and shaped using the flame, and the blowhole was cut off in cold working. Experiments were made with clear and colored glass to test optical effects of the pattern. Second, a press mold for cast glass was explored. A thick glass slab was cast into a steel frame. The tooled terracotta surface was pressed onto the glass slab for several seconds, then released. This generated a transferred pattern. Finally, a surface mold for set and press glass was tested. This thick glass slab was flipped onto the mold, allowed to set for a couple of seconds, and then pressed into the clay to pick up the tooling. As with our terracotta experiments, we hope to develop a feedback loop between the digital tooling of the terracotta panels, here used as molds, and the material behavior of glass. Our next step was to apply these sensibilities about digital materiality to a large-scale image with the goal of producing a surface that operates at both optical and haptic scales. Sampling the qualities of the most successful haptic surface tests, we assigned them to different regions within the image. In the final stages, we undertook a series of performance optimizations. Because of the robot's 6 axes of motion, you can have up to 5 tools on one end-of-arm tool and seamless changing between tools. We also calibrated the relationships amongst the impressions made by the larger tools in combination with detailing achieved by smaller tools to reduce tooling time and accelerate the process. Our KUKA robotic arm can move about 2.3 meters per second. Thus, our post-extrusion tooling procedure can easily keep up with the speed of industrial production. especially when executed in full automation in a closed cell system. Multiple robots can also work side by side to produce an endless variety of images, patterns, and textures. Through careful design of the end effectors and its operations, our team was able to create highly dense textures at high speeds. Ultimately, we aim to produce an image that performs beyond the surface. This piece aims to be experienced not as a static image, but in motion relative to its viewers. As we move towards the image, the figure begins to fade as its tactile qualities become more vivid. In the spirit of this virtual conference, we hope to bring this experience to you through our VR exhibition at www.hapteklab.com, where we invite you to explore the one-to-one scale mockup from a variety of distances. We also hope you will join us virtually in both the Creative Technology Labs at FCAD in Toronto at Ryerson University, as well as the Ceramic Studios at Syracuse University in Syracuse, New York, to see more of the processes, experimental failures, and successes of this project. If you are joining from home and have access to a VR headset, we invite you to click the icon on the top right-hand corner for a fully immersive VR experience. From a desktop or mobile browser, simply use the hotspots or the VR plan to navigate through the various virtual rooms. Ultimately, our process sets up the potential to integrate a new kind of digital craft into Boston Valley Terra Cotta's manufacturing pipeline, operating at speed in concert with the factory's production line and at sub-millimeter accuracy and repeatability. The robot becomes a critical partner in the manufacturing setting, offering the ability to create bespoke designs through an automated process, calibrated against digital craft and haptic feedback. This also offers the potential to be integrated with industrial manufacturing processes to make otherwise highly laborious detailing more widely accessible. Through programming and customized tooling, bespoke panels can easily be created without significant changes to the factory. We hope this process can unlock new possibilities for the craft of making within industrial ceramics production. In the next phase of this project, Haptek Lab aims to further develop this digital materiality at larger scales, exploring how designs translate across scales spatially, as well as from the tactile to the scenographic. Finally, we would like to acknowledge funding support from Ryerson University and Syracuse University, as well as in-kind contributions from the Creative Technology Lab at FCAD, Boston Valley Terra Cotta, Corning Museum of Glass, the Ryerson ARSID 3D Material Studio and Ceramic Lab, the Ryerson Collaboratory, and the Syracuse University Ceramics Department. Thank you for joining us for this presentation. We hope we will have the opportunity to share this work with you in person one day, and we're looking forward to the questions and discussion.